Hi everyone, welcome back. I was looking through my last video and realized that I went through it super duper fast. So I'm going to try to slow down a little bit for this second video, this companion video, where I go through things a little bit more slowly and give some more concrete examples. So let's go ahead and get started. Basically, in the last video, we wanted to give a concrete example of a non-trivial biological model that we can now understand using the tools that we've learned both in this class in terms of difference equations, as well as in your prior classes in terms of, well, a lot of linear algebra for the most part, some of which I assume you might not be so familiar with anymore, since it might have been a couple years since you've taken linear algebra. But first, we need to define our model. So like we said in the very first lecture, all models are wrong, some of them are useful. So we need to be explicit about what assumptions we're making. In this particular case, we start out by assuming that our population is closed to migration. This is just a simplification, so we don't have to worry about dealing with members of our population leaving a particular region. So we're basically just saying this is a closed system, we're not going to deal with the outside world at all. The second is that we're only modeling the females directly, and we're assuming that everything else is implicit. So it's not just females we're modeling explicitly, we're also only modeling females of reproductive age. So there are obviously females that aren't of reproductive age in the population. There are also non-females in the population, including possibly males. But we don't actually have to worry about them since they can't have children. And our model is only worried about increases to population number, and so we only need to worry about the members of the population that do actually reproduce. The other simplification is one here that is precisely because we are working with difference equations. And so both of these assumptions here are related to that, which is in order to work with difference equations, you obviously have to make your time intervals discrete. And for some insects, like for some organisms, like we were talking about, the time intervals really are discrete because of weirdnesses in the generations and the way they reproduce. But often for the mammals, for example, reproduction, or even most insects that just reproduce like continuously, you don't actually have these fixed time intervals. Instead, what we're doing is we are setting them. In some insects, you do have multiple different life stages, like you start with a larva, and then you go to a pupa, and then you go to an adult, or things like that. But we're not actually going to worry too much about the details here. This is still an abstract model, even though it's a little bit more concrete than some of the other difference equations we've been working with. Yeah, and so we also set it so that our time intervals are the same. Our time intervals are consistent with the individual age intervals. So this is a simplification, but it just means that as time goes from 1 to 2, your individuals age one stage. And finally, another simplification is that we can model the individuals in the same age group as having either the same reproduction rate or having the same reproduction rate on average. And so there's no additional structure on top of the age structure that we're adding to the system. Let's see. But yeah, now that those assumptions are out of the way, we want to turn these are assumptions on a model, and we want to turn that into math that we can then, apply our knowledge of difference equations in linear algebra 2. So the first thing is we have to have a state variable. Well, that's pretty obvious here. That's just the number of females in each age group. And so that's how we've defined this x sub I here. It's just, that's just the number of females in the ith age group at some time t. And then we also have a couple of constants that we have to specify into the model. So we have bi, which is the average number of newborn females produced by one female in the ith age group that survives the first time interval. The reason we need them to survive the first time interval is because we're not counting births that die immediately, since they don't survive to reproductive age, basically. And then Si here is just a fraction of the ith age group that survives until the I plus 1th age. So in every time interval, every individual has some chance of dying, and we're going to assume that that chance of dying is dependent, roughly speaking, only on which age group they're currently in. As individuals grow older, presumably they have a higher chance of dying, though you could imagine some setting in which maybe in the first couple age groups, you have a really high mortality rate, and then you have a low mortality rate, and then you have a high one again at the end. These just have to be some positive number specifying the fraction of the age group that does survive. Once you do this, well, then you can rewrite it all in terms of, well, difference equations. So the easy part's over here. So this is just the survival rate. As you go forward in time, the individuals in age group I turn into the individuals in age group I plus 1, and the number of them that do that survive to that, is just SI. The slightly more complicated one here is this birth rate. So the birth rate, for every single age group, the females there are reproducing and effectively sending some number of newborns down to the X1 group in the next time period. And so that's why we have this summation here. And as we did in the last lecture, excuse me, writing up all these things in difference equations is often made easy. These are all first-order difference equations, and so we can write them as a system, and then we can apply the techniques of linear algebra. So that's all we're, oh, that was the eraser. And so that's all we're doing here. So, oh, why did that jump up? But anyway, that's all we're doing here. We're rewriting these equations in matrix form. And when you write that matrix, you end up with something called the Leslie matrix here, which has the BI coefficients along the top row, and it has the SI coefficients along a diagonal in the lower left submatrix. So that's right here. And we don't have, we have zeros everywhere else. So this is the, also known as the projection matrix, because this matrix is what takes the population at time t to the population at time t plus 1. And so then, of course, if you just repeated the apply list, you end up getting the population at time x sub t. Another way of interpreting this is using something called a life cycle graph. So this is where we go from, this just has each of our different states, m, so these are our different age groups, and then we have the survival rates between the different age groups, so those are our SIs here, and then we also have the birth rates from the age groups, so those are our BIs. And all this graph says is it just shows us graphically, I mean literally graphically, how the number of people in one state affects the number of people in another state. And this is, because these arrows are pointed, this is known as a directed graph or digraph. Okay, so that's the general model. Now we're going to get into some more of the linear algebra of the system. So hopefully you learned about permutation matrices back in your linear algebra class, but just as a quick reminder, a permutation matrix just has exactly 1 in every row and column and zeros everywhere else. Let's give a couple examples. So for example, let me use green. I think I normally use green for examples. Well, a trivial permutation matrix is the identity matrix. So this is a permutation matrix because it has a 1 in every column and a 1 in every row, but zeros everywhere else. So there's exactly 1, 1. So what is not a permutation matrix? So, well, this is not a permutation matrix because you have 2 1s in one of the columns. So this is not a permutation matrix. Let's see, what about this one? Well, this is a permutation matrix because you have exactly 1 1 in every row and column. So let's give that a check mark. Let's say 0 0 0 1 0 0 1 0 0. This is again not a permutation matrix because you don't have exactly 1 1 in every row and column. One way of thinking about it is if you're a chess player, you can think of it as all the ways of placing, if you have an m by m chessboard, all the ways of placing m rooks such that none of them can in one move take any of the other ones. And one of the nice properties of these permutation matrices is that when you multiply the transpose of a permutation matrix by itself, you get the identity. And so permutation matrix's transpose is its inverse. And let's see that explicitly. And let me just give an example of that with our one good permutation matrix here. So if you take the transpose of this matrix, actually, the transpose of this matrix is just the matrix itself. That isn't always the case, but if you multiply those together, 0, 1, 0, 1, 0, 0, 0, 0, 1, well, in the first entry, we have 0, 1, 0 times 0, 1, 0, so that's a 1. This here, the 1s are in different locations, so that's a 0. Here, the 1s are in different locations again, so if you are multiplying those two together, 0, and so on. And this has a nice property because it means that we can if you recall from linear algebra, often you want to multiply a matrix on both sides by some other invertible matrix and its inverse. And that gives you similar matrices. And so that's precisely how we're defining a reducible matrix here. So a matrix is reducible if it's similar to a block diagonal matrix. So here, what we're saying is that if you can, and the thing about these permutation matrices is that they permute the rows and columns depending on whether you're writing it on the left or the right. And so in this case, what we're doing is we're permuting the rows and columns in such a way that we end up with this block diagonal structure. What just happened there? That we end up with this block diagonal structure, where of course our blocks A11 and A22 are of non-zero size. If you can do that, then it is reducible. If you can't do that, then it is not reducible, or irreducible. Now, the reason why this is important is because with reducible matrices, you can basically partition the influence of the different nodes into two different clusters, where one cluster doesn't influence the other one, but the other one does influence the first one. And so this has a nice interpretation in terms of the digraphs that we talked about a little bit earlier. But in order to do that, first we need to define a digraph. And that's basically just what we've done here. So a digraph, what we've done is for every one of our non-zero entries, we draw, so we have our m different nodes, and for every one of our non-zero entries, we draw a line from AJI, an arrow from I to j, assuming that it's non-zero. You could draw the arrows for the zeros as well, but that's just not useful because there's no influence there. So now we define a digraph as irreducible. We define a digraph as strongly connected, basically if you can get from one place to another, from any place starting point to any other ending point by following the arrows along a path. And it turns out there is a very nice theorem relating the strongly connectedness of a digraph with the irreducibility of the matrix that generated it. So a digraph is strongly connected if and only if A is irreducible. Okay, so let's give a quick proof sketch of theorem 1.2, just so that you guys are aware of how this works. So let's start with the first case. So case 1, suppose A is reducible. So one of the things you'll notice is that that means that A has this block diagonal form from up here, A11, A12, 0, A22. So A11, A12, 0, and A22, where these are all block matrices, and A11 and A22 are of non-zero size. So one of the things that you'll notice is that if there's a non-zero entry, let's see, if non-zero entry AJI, that means there is an edge from I to j, right? And one of the things that if you study a little bit of graph theory, you'll know, and that's not that hard to figure out, is if we have, suppose we had another matrix, so consider A squared. So if we have a non-zero entry, let's call this a squared sub ij. That means there is a path of length 2 from I to j. So this is something you should verify if it doesn't make sense to you. But of course, and it turns out that if you're looking at this sort of path, you can take this to any number. Let's call it, what variables haven't I used? Let's call this k. So if the non-zero entry of a k sub ij, that means that there is a path of length k from I to j. And this is super nice, because we know that that means that in order for the digraph, so in order for the digraph of A to be strongly connected, we need a path of some length k from I to j for all I and j. But we know that this is a block diagonal matrix. So A squared is going to be equal to A11 squared. Well, let me write this out. So A11, A12, where these are all block matrix blocks, times A11, A12, 0, A22, which is going to be equal to A11 squared. This is going to be A11, A12 plus A12, A22, 0, and A22 squared. You'll notice that this 0 remains. And because that 0 remains, and by induction, we know that a to the k is equal to A11 to the k, something here. We don't know what it is. I mean, we can compute what it is, but it doesn't really matter. A22 to the k, and 0. So for any k, there's no path from node m to node, from node 1 to node m. 1 to node m. You'll notice that I was a bit fast and loose here. I said that if A is reducible, then A is equal to this. Well, that wasn't quite how we defined it. What we said is that A is reducible if there's some permutation of the rows and columns that puts it in that form. But, of course, that's just equivalent to a relabeling of those vertices. And so we can say without loss of generality, A has this form. And so now we'll note that there is a 0 here. This is entry A to the k sub m1. So that's why we conclude that for any k, there's no path from node 1 to node m. Hence, plus if A is reducible, plus if A is reducible, then it is not strongly connected. Okay, and then of course we need to go the other direction as well. So let's give a case 2. So suppose the digraph is not strongly connected. Suppose digraph of A is not strongly connected. Well, if it's not strongly connected, then clearly there are, starting with any labeling, so pick a random node, pick an arbitrary node and label it 1. Arbitrary node and label it 1. So if it's not strongly connected, then you can't get from any point to any other point. So without loss of generality, assume that there exists no path from 1 to some other node. In fact, we can say that in fact, we can label it so that the first k nodes, there is a path from one to those nodes, and for the next m minus k nodes, there is no path. Can partition the nodes by whether or not you can reach it from 1. Oh, wrong color. By whether or not you can reach it from node 1. Okay, but once we've done that, then the matrix A, under that load renabling, but then we clearly can't reach it in one step, right? If you can't reach it ever, then you clearly can't reach it in one step. So the matrix A has the form, well, we know that all the things that A can reach are here. So there's something here, here, all the way down to here. So these are things that a matrix A can reach. And then zeros here for all the things that matrix A can't reach. And you'll note that everything up here, those are things that matrix A can reach. And so if matrix A can reach it, then those nodes obviously can't reach the nodes in the other set either. Because if they could, then you could go from A to one of those nodes and then go all the way to the other side, to the other set. So clearly, for all of these nodes, so there is some block, there's some block here, so there's some square block here. And these are all the nodes that can be reached. And clearly those have to not be able to reach anything down here. And so it doesn't matter what we have here, but this is block diagonal under that node relabeling, where the first half are nodes reachable from node 1. Plus, we know that the A must be reducible. So that proves both halves of this theorem. So therefore, if the digraph of A is strongly connected if and only if A is reducible, which provides a nice connection between the graph formulation and the matrix formulation. So now let's take a look at what this means for the Leslie matrix that we discussed earlier. So going back to our biological population model, well, remember we said that this matrix here, well, we want it to be, and if we want it to be an irreducible matrix, we need this life cycle graph down here to be strongly connected. Well, as we said in the previous lecture, well, in order for it to be strongly connected, we need you to be able to reach every node from any other node. Now let's suppose that we get rid of, let's not use the eraser, let's use the red marker. So if we erase this edge, then all of a sudden you can't reach node M anymore, and therefore it's no longer strongly connected. So you need the survivals to be positive for all of these S's here. Now this is not so big of a requirement, because if the survivals weren't positive, then you wouldn't have any individuals in the state anyway. So if S sub M sub minus 1 were equal to 0, well then you wouldn't even bother writing state M because you would have no individuals in that state. Therefore that's not such a big deal. And additionally we need that if we want the entire thing to be strongly connected, we need this Bm to not be equal to 0. Since if this Bm is not equal to 0, then you can't get anywhere from m, and so then again, it's not strongly connected. But assuming that both of those are true, assuming that your Bm is not equal to 0 and your survivals are non-zero for every one of your life stages, well, then it's pretty obvious that the life cycle graph is strongly connected, and therefore the Leslie matrix is irreducible. And this will come into handy later when we show some of the properties of irreducible non-negative matrices, which the Leslie matrix is an example of. Going back down here, the Frobenius and Perron theorems are precisely the ones that we're going to now apply to our Leslie matrix. So the Frobenius theorem, what happened to my F flare? So for the Frobenius theorem says that if you have an irreducible and non-negative matrix, well, then the dominant eigenvalue is positive. So that's what I'm saying here with the eigenvalue being equal to the spectral radius. Remember that the spectral radius is just the absolute value of the biggest eigenvalue. And so what we're saying is that the biggest eigenvalue is actually a real number, and it's positive by saying that lambda is equal to the spectral radius. And then it has multiplicity 1. Furthermore, lambda then also has a corresponding eigenvector with positive components. The Perron theorem is a little bit more restrictive. It says that if A is strictly positive, so if every one of the entries is positive, then the same lambda that's equal to the spectral radius is a strictly dominant eigenvalue of multiplicity 1, and lambda has a corresponding eigenvector with positive components. Note that if A is a positive matrix, well, then it's clearly irreducible, because no matter how you shift your no matter how you permute your matrix, every entry is going to be positive, and so you can't turn it into a block diagonal with zeros anywhere because there are no zeros to begin with. And it's also non-negative. And so the Perron theorem is implied by the Frobenius theorem, though it's a little bit, just because the conditions are stronger on it. And it's not quite implied by the Frobenius theorem because you get the additional property that it's strictly dominant rather than just dominant. But other than that, it's almost implied by the Frobenius theorem. It turns out that this is a little bit tricky to prove, so I'm not going to go through the entire proof, but I will go through a partial proof of the Perron theorem just to give you a sense of the linear algebra that's involved. So now actually proving the Frobenius and Perron theorems in their full generality is a little bit complicated. So we're not going to actually cover all of that in this class. I'm just going to give you a brief proof for part of the Perron theorem. Basically, I'm going to prove that if a matrix is positive, then there is a strictly maximal eigenvalue for the matrix. So let me write that out. Let's give ourselves a little space here. So this is going to be, proof sketch for existence of strictly dominant positive eigenvalue of positive A. Okay, so now the first thing we're going to do is we're going to normalize the matrix so that the largest eigenvalue has modulus 1. So without loss of generality, we're going to assume that rho of A is equal to 1. And if not, consider A divided by rho of A. And then of course, if our other matrix doesn't actually have spectral radius equal to 1, we just divide it, show everything so that it has exactly 1 as its eigenvalue, as its strictly dominant eigenvalue, and then multiply it back by rho of A to get back to our original matrix. So we can just, but this makes the proof a lot simpler. Okay, so now if the spectral radius is equal to 1, then there has to exist some lambda, eigenvalue lambda, exists an eigenvalue lambda with lambda, the modulus of lambda, the absolute value of lambda is equal to 1. Now, suppose that there exists, okay, so clearly there's one that's equal to 1. Suppose lambda is not equal to 1. So clearly there's one with the modulus of 1. Suppose that lambda itself isn't equal to 1, however. So it's some other complex root that falls on the unit circle with absolute value 1. So if we draw that out, so this is the complex plane, so this is the real line, this is the complex line. We know that we have a root, so this is the unit circle. So unit circle. Oh, and we're supposing that we have some root there. So let's say our lambda is there. Doesn't matter where it is. It's just some lambda that's on the unit circle that's not equal to 1. But if it's not equal to 1, then suppose then there exists a positive integer m such that, well, A is a positive matrix, so AM is positive. And we know that the real part of lambda to the m is negative, so it's less than 0. Why is that? Well, that's because whenever you take lambda to the m, you're basically going around the circle. So if you go around it again, this is lambda squared, etc. So you can keep on going around, and if you started at 1, you'd never go anywhere. But if you don't start at 1, then as you go around the circle, at some point you'll get to the negative side of the real line. And so this is why there's some m such that the real part is less than 0. Let me give myself a little bit more space here. Okay, so if the real part is negative, now let's do something else. So now let epsilon be half the smallest diagonal entry, half the smallest diagonal entry of a to the m. A to the m is a positive matrix, and so epsilon is also a positive number. Note, epsilon is greater than 0 because am is positive. Okay? Then define another matrix, T to be equal to am minus epsilon I, where I is the identity matrix. And this is also greater than 0. Because epsilon is half the smallest diagonal entry, so if you subtract that out, here you're basically subtracting the entire diagonal of am by this epsilon, and so that still stays strictly positive. And so once we've done that, suppose that we had some vector. Actually, let's. So if ax is equal to lambda x, so if x is an eigenvector, then we know that a to the m of x is equal to lambda to the m of x, right? But then that implies that lambda to the m minus epsilon is an eigenvalue of t. But then that implies that the modulus of lambda to the m minus epsilon is greater than 1. Why is that? Because if we have some, if we have some lambda, let's say that's, maybe, let me just redraw all that. So if we have some lambda that's on the units, let's say this is lambda to the m on the unit circle. Let's see, this is the real axis, this is the complex axis, and you're subtracting it by a positive number that pushes it in this direction. So this here is lambda to the m minus epsilon. So we're pushing it in the minus direction along the real axis, and so you'll see that it's outside of the unit circle. So therefore the modulus of lambda to the m minus epsilon is greater than 1. Now, this actually implies a contradiction, right? Because that implies that lambda to the t is less than or equal to, we know that lambda to the t is, rho of t, the spectral radius of t, is greater than 1. However, we also know that the spectral radius of t is less than or equal to the spectral radius of a to the m. So this is by Gelfand's formula, which I'm not going to prove. Gelfand's formula. But of course, this is less than or equal to rho of a to the m, which is equal to 1. So this is a contradiction. And that, of course, implies that lambda has to be equal to 1, and there are no other eigenvalues on the unit circle. Okay, and of course, if your original spectral radius wasn't equal to 1, then you just scale down and scale back up. So that completes that proof sketch. So now, although we just proved the Perron theorem for, or we proved the existence of a strictly dominant positive eigenvalue of positive matrices A, let's go back to the general case where we have an irreducible and non-negative matrix A, as in the Frobenius theorem. In that case, because it's only a dominant eigenvalue and not a strictly dominant eigenvalue, you could have other eigenvalues that have the same modulus, so the same maximum modulus, but they're just not positive. They have some complex value, or maybe they're negative. And we can measure how much that is the case by asking how many eigenvalues it has of maximum modulus. And so if it has, so we'll say that it has h eigenvalues of maximum modulus, and if it's primitive, if it has only 1. And it's imprimitive if it has more than 1. And this turns out to match up nicely. So in the case of the strictly positive irreducible matrices, well, clearly those are primitive because we just proved that there can only be one maximum modulus eigenvalue. Unfortunately, that's not generally the case, and so we want to know some conditions under which the positive matrices are also irreducible and primitive. And so that's what we prove in theorem 1.5, or what we state in theorem 1.5, that if A is non-negative, so if A is non-negative, then A is primitive if and only if there exists some power of A, so A to the p for some positive integer p, such that that is strictly positive. So basically what we're saying is that an irreducible matrix is primitive if there's some power of it that is positive, and then you can sort of see how intuitively this makes sense, because then you would be in the case of the Perron theorem, and of course the eigenvalues of A and the eigenvalues of A to the p are very closely related. So if there's an eigenvalue of A to the p that is strictly dominant, well then if you take the pth root of that, then that would have been whatever that was in the original matrix A would have been strictly dominant in A. I'm not going to write that out explicitly, but that's the general intuition behind that. Moving back to some of the biology though, we are now going to introduce something called the inherent net reproductive number. As I mentioned in the last video, you guys might have heard about these R naughts from back in, I guess, last March now, when we were talking about flattening the curve for epidemic reproduction. So here we're not talking about epidemics, we're talking about a population of individuals reproducing, but it's the same concept. So R naught is the expected number of offspring for an individual over its lifetime. In the case of epidemics, it's the expected number of people that the average person infects over the course of their infectious period. Here we're just saying, well, for a female individual in our population, what's the average number of female children they have? And so we can, this turns out in the Leslie model to be really easy to compute because how many individuals can they have? Well, this is a female that has at least survived the very first stage, and so they have children, some number of children, B1, in their first time stage of life, and then in their second stage of life, they have B2 individuals. But not all of the females survive to the second stage, and so that's why you have to multiply by S1, which is the probability that that female survives to the second stage. And the probability that it survives to the third stage is S1, S2, and then you multiply it by the number of individuals that are born to the average female in their third stage of life, and so on, all the way to the mth stage, which is the last reproductive stage of life. This is a simple summation and gives us the basically the way the population is growing or not. And we can nicely connect this together with our original Leslie matrix. So it turns out that if our Leslie matrix is irreducible and primitive, then we have this strictly dominant eigenvalue, lambda 1. And if lambda 1 is equal to 1, then so is the reproductive number. If lambda 1 is greater than 1, then the reproductive number is also greater than 1. And if lambda 1 is less than 1, the reproductive number is less than 1. So now, what does this mean exactly? So if lambda 1 is equal to 1, that means that as you apply your matrix to the population size, and suppose that you're at your eigenvector associated with lambda 1. So that's your population distribution. Well, then that's unchanging. And so effectively, that's what we mean by saying that the reproductive number is equal to 1. Because once you've reached that eigenvalue state, eigenvector state, which you are going to asymptotically, since it's the dominant eigenvector, well, that determines the population size. And so the reproduction, so the population size is stable. So over the lifetime of a female, it produces one child. Now, if over the lifetime of a female it produces more than one female child, then obviously the population size is going to grow, and your lambda 1 is going to be greater than 1, and vice versa if lambda 1 is less than 1. And if you just look at that eigenvector, that tells you exactly what the stable age distribution is. So if you let time run for a very long time, eventually the population will stabilize in terms of age. So there will be X number of people in stage 1, X number of individuals in stage 2, X number of individuals in stage 3, or X1, X2, and X3 in stage 1, 2, 3 respectively, and so on. And that'll be stable as time goes on because the population will be stable. In every stage of life, the same number of people who are entering that stage of life as are leaving or dying, as are leaving that stage of life, etc. And so everything is in balance. Yeah, and there are just a couple other criteria that we can use to determine if an irreducible matrix is primitive. And so it turns out that if the birth rates satisfy the following, the relationship of the greatest common divisor of the index divides all the birth rates that are greater than 0. If the greatest common divisor is equal to 1, then the matrix happens to be irreducible. So let's see an example, going back to the Leslie matrix, going back to a concrete, simple Leslie matrix. So this is going to be, let's see, example 1.20. So let's let L be equal to 0, B2, S1, and 0, where B2 and S1 are greater than 0. And so if you draw out the life cycle diagram, this goes from stage 1 to stage 2 with survival rate S1. And we have B2 for the birth rate from females in stage 2 back to stage 1. And we have no birth, in stage 1, they're not reproductive, and so you don't have a B1. So in the general Leslie model, you might have a B1. We don't have that here. So this makes it a super simple, non-trivial example of a Leslie matrix of a 2-stage population. So now, what can we do with this? So clearly, L satisfies the Frobenius theorem, because the life cycle graph, is strongly connected. Okay, and that's pretty easy to see. You can go from 1 to 2, and you can go from 2 to 1. And those are the only two states of the system. Which, however, L is imprimitive. And there are two different ways of seeing that. So one way to see that is to use to see this. See this is to use theorem, I think it was 1.5. So for theorem 1.5, we needed, let me find it again. So for theorem 1.5, we said that A is primitive if and only if A to the P is greater than 0, is strictly positive for some P that is for some P that happens to be a positive integer. So, well, L clearly doesn't work because L is equal to 0, B2, S1, 0. L squared, well, if you multiply that out, that's going to be 0, B2, S1, 0, 0, B2, S1, 0, which is going to be equal to, well, unfortunately, this term here is going to be B2, S1, this term here is going to be 0, 0, and again, B2, S1. Which also isn't strictly positive because it has two zeros. And it turns out, that L to the P will always have zeros. And you can multiply out and see it that way. Another way of seeing it, another way to see it is to explicitly compute the eigenvalues. And it turns out the eigenvalues are lambda 1 and 2 are equal to plus or minus the square root of B2 S1. And that's pretty easy to compute. And so in this case, both of them have the exact same modulus because they're the positive and negative of the same number. Okay, so it's imprimitive. And we can also see it another way. So let's see. So it's imprimitive, yet another way to see this is using theorem 1.7. So the greatest common divisor of 2 is equal to 2. See? So what exactly did this theorem mean over here? Well, it's the greatest common divisor for I such that bi is greater than 0 for the entire set, right? And so in this particular case, what we're saying is, well, we only have one bi that's not equal to 0, and that's when this bi here, so that's b2. And since b2 is the only one that's not equal to 0, we're only taking the greatest common divisor of the set 2. And the greatest common divisor of the set 2 is just equal to 2, which implies that L is imprimitive. So we have a lot of tools for seeing that L is imprimitive. Yeah, I think I will end my lecture there. Once you've figured out that something is imprimitive, then you can't use the nice results in theorem 1.6 to show what the reproductive number is, though there are more in-depth things you can do. But I think that'll end my lecture, so I will see you in the next video.